Good afternoon, everyone. Today I'm excited to be presenting our work, Wizundry, an innovative web-based platform that enables multiple wizards to collaborate remotely in real time to simulate an increasingly advanced speech interface system. First, let's provide some background about the Wizard of Oz. Wizard of Oz has been leveraged for decades across numerous domains like human-computer interaction as a methodology to prototype and evaluate interactive systems, especially speech interfaces. It involves having a person referred to as the wizard behind the scenes who can monitor the user's input and manually control the system's responses on the fly to simulate intelligence. Wizards enact dialogues, execute commands, and adapt reactions to provide the illusion of a fully capable system. However, as users' expectations regarding artificial intelligence and virtual assistants continue to expand exponentially in terms of capabilities, this poses substantially greater demands on solo wizards to dynamically handle open-ended, complex, and sophisticated interactions. This level of sophistication stretches solo wizards' abilities to simulate systems that can meet these demands. However, simulating the more intelligent behaviors expected from AI places great cognitive demands on solo wizards. Some prior research has explored engaging multiple wizards, primarily to handle multimodal interfaces by having wizards control different modes separately. This is where the multi-wizard approach provides the necessary manpower to distribute workload and enable simulation of sophisticated capabilities like real-time natural language processing, multitasking, and personalized responses. However, effective strategies for team collaboration are still unknown when it comes to multi-wizard. Besides, multi-wizard provides opportunities to rapidly prototype and test a wider range of AI capabilities by combining multiple human intelligences. But, whether dividing workload across multiple wizards can effectively reduce cognitive demands, prevent overload, and improve the realism of complex system simulations. Is this actually useful? Is adding more people the best way? The multi-wizard concept has huge potential but remains understudied, warranting systematic research to validate the approach, reveal effective practices, and accelerate innovation in simulated speech interfaces. Our work aims to build on and extend prior remote, open-source WAS platforms by adding integrated supports for collaborating wizards power, divide and conquer, and their personal roles. And coordinating, aligning multiple wizards same time on a shared prototype. We thus developed the system to explore. How do multiple wizards collaborate while simulating a speech-based text input and editing task? How collaborative system functions might assist multiple wizards in developing collaborative strategies? How do wizards modify their collaborative strategies according to the end user's responses? Based on the design goals for collaborative simulation and investigating collaboration strategies, we also want to use this platform to evaluate multiple wizards' approach. Here are 3 core research questions. First, is utilizing a team of multiple wizards to jointly simulate advanced speech interfaces with greater intelligence and sophistication actually feasible compared to solo wizards? Second, can a multi-wizard platform enable rapid iteration of simulated interface concepts by empowering wizards to quickly test out and pivot between different approaches to dividing up responsibilities and coordinating workflows to align efforts? And third, can taking a collaborative multi-wizard approach provide valuable insights into improving the overall end-user experience by allowing wizards to handle a wider range of demanding situations? In order to explore 2 types of research question, we developed the multi-wizard platform. Now, let me provide an overview of Wizundry. It is a web-based system that incorporates speech-to-text transcription and text-to-speech technologies. The wizard interface needs to provide numerous features specially designed to support fluid coordination, awareness, control, and task division capabilities to collaboratively simulate intelligent system behaviors. In the wizard interface, it offers a collaborative text editor that enables multiple wizards to jointly transcribe audio streams of user dictation as well as edit and reformat the resulting text in real time. For collaboration awareness, it provides collaborative cursors and name tags that let wizards visually track each other's location and current actions in the shared workspace. For flexible control, wizards can turn on off the microphone to manage when to process user speech as well as utilize editable speech boxes to efficiently simulate system-generated verbal responses and feedback. These features aim to provide a streamlined environment to explore different approaches to coordinating and dividing up simulation responsibilities between the wizards. For control, wizards can turn on off the microphone to manage when to process user speech as well as utilize editable speech boxes to efficiently simulate system-generated verbal responses and feedback. These features aim to provide a streamlined environment to explore different approaches to coordinating and dividing up simulation responsibilities between the wizards. Meanwhile, the end-user interface focuses on enabling natural interaction flows and providing intuitive system feedback. The main features include a smart dictator panel that leverages speech recognition APIs to simulate transcription of the user's natural language dictation into text, mirroring capabilities in modern systems. Visual indicators that display the current states of the microphone and speaker to represent when the system is actively listening or speaking. And real-time updates that reflect changes made by the wizards behind the scenes and maintain synchronicity. Together, these aim to create a believable system prototype from the end-user's perspective. We conducted 2 user studies analyzing the collaborative multi-wizard experience from both the wizards themselves and end-users' perspectives. The findings provide compelling insights into multi-wizard collaboration dynamics, strategies, challenges, and impacts on the end-user experience. Now, I describe the first user study conducted, which focused on comparing solo wizard versus dyad wizard configurations for a text dictation task. Focused on comparing solo wizard versus dyad wizard configurations for a text dictation task. 12 participants were recruited to take part, acting as wizards, first individually and then in randomly paired teams of 2. The dictation task involved flexibly composing and editing text by simulating an intelligent dictation system capable of handling natural voice commands. A researcher acted out the role of the end user, following a set of prepared dictation scripts and commands over audio channels. The study followed a within-subjects design with one condition: the number of wizards, which alternated between solo and dyad. Some key findings that emerged were: 5 main collaboration strategies materialized, can see in our graph, such as a content-based approach. Adapting approaches was common until settling on mutually agreeable responsibilities. Mixed sentiments on the benefits of having a second wizard, some felt aided, others hindered. Uneven division of labor hampered effectiveness due to uncertainty about responsibilities. The platform did enable rapid iteration of simulated interface concepts by empowering wizard teams to quickly construct and test strategies. Dominant personalities helped reduce coordination conflicts. Based on the first user study findings, we implemented several iterations to the system. Include improved real-time editing capabilities using a pop-up bubble menu. Developed a modular interface design to flexibly combine advanced features, as the right side figure shows. Provided separate predefined roles and interfaces to clarify responsibilities. Added new intelligent text processing capabilities like highlighting and summaries. These changes aim to better support multi-wizard coordination, awareness, and task focus. Then we conducted a second study to evaluate the multiple wizards concept. This time with 12 new participants organized into 4 groups, comprised of 3 wizards each. Their collaborative task was to simulate an intelligent dictation system capable of processing interview transcripts in real time, including capabilities like labeling and summarizing. There were 3 distinct wizard roles specified: dictation, labeling, and highlight plus summarize. The wizards needed to coordinate across these divergent roles while responding to end-user requests. In terms of devising collaborative strategies, I found 3 primary approaches emerged. Pipeline: wizards worked sequentially, with each building on output from prior roles. Coordinated: the dictation wizard set the pace and rhythm for the team. Spontaneous: wizards fluidly assisted each other beyond just their own role. The strategy aligned with how roles were divided up and integrated, which significantly impacted perceived effectiveness. In general, temporal demand remained consistently high across groups as wizards raced to keep pace with the evolving conversation. The dictation wizard often became the bottleneck, as downstream roles relied on their output. Coordinating handoffs and transitions between roles added substantial cognitive effort for some groups. But perceived collaboration effectiveness increased when earlier wizards proactively supported later wizards' work. For end-user experience. End users needed more ways to communicate context, correct issues, and guide wizards, but struggled to fully satisfy all user requests despite feedback when they act as wizards. In conclusion, our Wizundry platform offers the first open research toolkit tailored specifically to multi-wizard collaboration, dynamic task coordination, and optimizing the end-user experience. Through 2 user studies, we revealed promising new cooperation strategies, challenges, and design insights that can power the next generation of speech interfaces and the realism of future AI simulations. Overall, Wizundry enables the research community to further push the boundaries of Wizard of Oz realism for voice interfaces, and uncover better ways to simulate advanced AI capabilities through coordinated teamwork. For this research, employing a collaborative multi-wizard approach enables simulating more advanced speech interfaces and functionality than possible with solo wizards. However, coordinating multiple wizards introduces inherent challenges that warrant further research. The Wizundry platform provided an effective means for rapid ideation, iteration, and evaluation of intelligent speech interface concepts by distributing efforts across a wizard team. I believe these findings make important strides towards guiding fellow researchers in adopting multi-wizard approaches in their own prototyping work and offer valuable new insights into designing mixed initiative systems. Huge thanks to my co-authors and reviewers. Please check out more detail in our paper and feel free to contact me for further questions.